9th standard ICSE chemistry from the textbook of Anita Prasad. Chapter 5, the periodic table of elements. The first page, mark it as read. It's a history of various ways of classifying elements. Lavoisier segregated elements into metals and non-metals, but this was not adequate because the number of metals was far more, and there were some metalloids as well. Then Doberiner classified elements into triads, which we'll study in detail shortly, but soon this was discarded. Then Newlands, he had a law of octaves, which was pretty successful, but it ran into trouble and even it was rejected. Then Mayer, he classified on the basis of their valencies. Then came Mendeleev. He is called the father of the periodic table. He was the first person to make a periodic table, a table with columns and rows, and which showed a periodic repetition of properties. The modern periodic table is based on his work, and that was given by Moseley. First, Dobrynin's law of triads. He arranged some elements in groups of 3 called triads, which had similar properties like lithium, sodium, potassium, chlorine, bromine, iodine, in the increasing order of their atomic weights. And he saw that the atomic weight of the middle element is approximately the mean or average of the atomic weights of the other 2 elements. So he made it into a law, which was quite interesting. For example, these 3 are alkali metals. They have similar properties. All of them react violently with water to give hydrogen. They are monovalent. They are alkaline earth metals. Alkali and alkaline earth metals, they are called so because when they are dissolved in water, they give alkalis, that is bases which are soluble in water, like lithium hydroxide, calcium hydroxide. Although calcium hydroxide is only partially soluble. They form basic oxides, and they have valency 2. Their salts are found in the Earth's crust. Halogens, salt generators. They are all non-metals. They react with water to form acids, and they have valency 1. But there were limitations with Dobernin's triads. It worked for very few elements, not all the elements known at that time. And there were elements which were similar, but there were more than 3. So we cannot put it into a triad. Also, it did not work for some triads where the properties were same, but then the atomic weight was very different from what was predicted. For example, in the triad of fluorine, bromine, and chlorine, the average should be 49.5, but chlorine's atomic weight is 35.5. So it was a flop. So these are the triads he gave. 6 triads. So that's 18 elements. That's it. No need to learn this. Cancel it. Next, Newton's law of octaves. Octave is known from the musical scale. There are various frequencies, various notes. Like the Indian note is sa re ga ma pa dha ni sa. This sa is a multiple of sa. So every 8th note is a multiple of the first note. Similarly, when elements are arranged in their increasing order of atomic weights, like this, every 8th element is similar to the first one. For example, if I start from carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminum, silicon. I have a cold, otherwise I sing very well. Silicon is similar in properties to carbon, valency 4. Well, at that time, noble gases weren't even discovered. They were discovered a little later. So this is the law which has to be learnt. He had arranged the elements in increasing order of atomic weight, which was a nice idea. And every 8th element, if I start from lithium, the 8th element will be sodium, which will have similar properties. But again, it was rejected because it had some demerits. It did not work with heavier elements. It worked only with the first 20 elements. And at that time, all the elements weren't even discovered. ion, which resembles cobalt and nickel, was placed far away from them. So there were some advantages. For example, it helped us to detect a periodic pattern, which is also visible in today's periodic table. And then came Mendeleev onto the scene. He was a Russian chemist. He gave a law. He stated that the physical and chemical properties of elements are periodic functions of their atomic masses, which means that if you arrange the elements in increasing order of their atomic weights, then you will see a periodic repetition of their physical and chemical properties. So this was his original table with groups and columns. That's why it's called a table, and periodic because the properties are repeated periodically. Lithium, alkali metal, alkaline earth metal, metalloid, non-metal, halogen, noble gases were not discovered at that time. And then again, alkali metal, blah 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 blah, again alkali metal. So there's a repetition. The valency is being repeated. The oxidizing or reducing property, the metallic characteristic is being repeated. If I start from fluorine, halogen, then strong metal, weaker metal, metalloid, non-metal, halogen. So again, there's a repetition. Hence, it's called a periodic table. As you can see, his groups had subgroups also. Like this group 3 has some elements on the left and some on the right. Also notice that he had left blank spaces for elements which weren't even discovered yet. Because if he would put this in this group, then the properties weren't matching. So he thought that perhaps I should keep this in this group because the properties are matching. And he predicted that some element with properties similar to aluminum is not yet discovered. He even predicted the atomic weight, and that was his genius. Even the chemical properties which he guessed were very close to the properties once these elements were discovered. And the use of this table is the elements of the same group have same properties. He predicted the properties of some elements and he called them eka-silicon, eka-boron and eka-aluminum. And later they were called germanium, scandium and gallium respectively. But again, there were some problems in this table. First of all, the merits of this table. It helped in systematic study of elements, because once we group them into a single category, we can learn all of their properties together. For example, we know that alkali metals have valency 1, hydrogen is not a metal. They are highly reactive with water, they form alkalis, they are good reducing agents, good conductors of electricity, they are soft and can be cut with a knife. So it's so easy to learn the properties altogether. Similar to classification of plants and animals. Correction of atomic masses. When he found a discrepancy in the arrangement, he predicted the correct atomic mass of certain elements. For example, for beryllium, he realized that it cannot be 13.5 because if it's 13.5, then it should be kept later. But beryllium should belong to group 2, which means atomic weight should be less than that of boron. And when the scientists recalculated, indeed it was found to be 9, not 13.5. So he had so much confidence in his theory. Even atomic weights of gold, platinum were corrected like this. He predicted undiscovered elements. Noble gases were discovered very late because they are very inert and not reactive. But Mendeleev could easily accommodate them. He could just add the periodic table in the 0 group. In the modern periodic table, this group is kept at the end. It's called the 18th group. But he called it a 0 group because valency is 0, which is quite a remarkable feature of this table. But the problems were, first of all, position of isotopes. For example, carbon has a few varieties, few isotopes. We have carbon 12 atomic weight and carbon 14 atomic weight. Atomic number is same, 6. But carbon 12 means it has 6 protons and 6 neutrons, and carbon 14 means it has 6 protons and 8 neutrons. So according to his law, carbon 14 has more atomic weight, so it should be kept after carbon 12. But that's ridiculous because all isotopes have same chemical properties, so they should come together in the same group. So that's a contradiction to his law. Today this problem is solved because we know that atomic weight is not the fundamental property of an element, atomic number is. So if we focus only on atomic number, on which the modern periodic table is based, then all the isotopes belong to the same groups, so the problem is solved. Next issue is the position of rare earth metals. There were some rare earth metals called lanthanide series, which could not be placed properly because all of them have same properties, so they should belong to the same group, but they have different atomic weights. So we'll see soon how this problem is solved in the modern periodic table. Then there were some anomalous pairs. For example, argon 39.9 atomic weight is placed before potassium 39.1 because only then will it be placed in the same group. If I keep potassium first and argon later in ascending order of atomic weight, then the properties won't match. So he had to break his own rule. But a law which has exceptions is not a good law. Position of hydrogen was an issue because hydrogen sometimes behaves like alkali metals. It loses electron to become electropositive, and sometimes it behaves like the halogens, group 7, because it can gain an electron and become an anion as well. This problem hasn't been solved yet. Next, the discovery of atomic number. First paragraph, mark it as read. Now, the modern periodic law is the same as Mendeleev's periodic law. The only difference is that atomic weight has been changed to atomic number. And atomic number is a fundamental property because atomic number decides the electronic configuration, and the outer electronic configuration, that is the valency, decides all the chemical properties. Atomic weight is different in isotopes because number of neutrons are different, but number of neutrons don't affect chemical properties. They simply affect some physical properties like density and etc. So that is why atomic number is a fundamental property. So mark this as a give reason. So they solve many problems because now argon can be before potassium because its atomic number is less than that of potassium, even though its atomic weight is more than that of potassium. Also, hydrogen's atomic number is 1, so now we have fixed its position to be in group 1, although it is not an alkali metal. Isotopes have same atomic number, so we can fit them into one spot. Rare earths, well, we had a different fix for it. We simply made an asterisk and wrote the list at the bottom. So the modern periodic table, what a beautiful table. It has 18 groups and 7 periods. The group number gives us an idea about the number of valence electrons, which can tell us the valency. The period number will tell us the number of shells in the atom. But remember, shells have subshells as well, S, P, D, F, which you'll study in college level. An atom is nothing like this. The real atoms are very weird, and it's not for school level. These are just basics to learn right now. Notice that most of the 118 elements discovered so far are metals. Some are metalloids, this ladder. These are the non-metals, very few. These are halogens, inert gases. Organazon is the latest element discovered and named. Group 1, all of them have valency 1, 2,1, 2,8,1, 2,8,8,1, 2,8,18,8,1, and so on. So all of them have the same valency, all of them have the same properties. Group 2, alkaline earth metals, valency 2. Groups 3 to 12 are blank for the first 3 periods. So after group 2, we jump to group 13. Boron, aluminum have all valency 3. 3 valence electrons, 2,3, 2,8,3. Group 14, valency 4. Group 15, 5 valence electrons, but valency 3. Because nitrogen 2,5 would like to share 3 electrons or gain 3 electrons to become stable. Group 16 has 6 valence electrons, so valency 2. Group 17 has 7 valence electrons, so valency 1 again. Fluorine 2,7, chlorine 2,8,7. They would share 1 electron or gain 1 electron to become stable, like the nearest noble gas, which is neon and argon, respectively. They have a complete shell. They have 8 valence electrons, octet, except helium, which has a duplet, 2 valence electrons. They don't react, they are stable. From period 4 onwards, even the groups 3 to 12 are filled with transition elements. A transition from metallic properties on the left to non-metallic properties on the right. What is unique about these transition metals is that they show variable valency. They don't lose electrons only from the last shell, like these group 1 to 13 to 17 do, but they lose electrons even from the penultimate or second last shell. In fact, elements 57 to 71, these 15 elements, which are similar to lanthanum, and they are called lanthanide series, they are rare earth elements. They all have the same properties. They all belong to group 3 and period 6, but we can't fit 15 elements in one box. Hence, we have separated them out here. Although I would have built a 3D model and placed all 15 elements like a tower on top of this. Similarly, the actinide series, the radioactive elements, these 15 elements are like actinium. They all belong to group number 3 and period 7. And they have last 3 shells incomplete. These transition metals form salts which are colorful, unlike the other elements. Metalloids have properties of both metals and non-metals. Boron has valency 3, yet it's a metalloid because of its small scale. Its small size, due to which there is a greater nuclear pull on the outermost electrons. So they are not able to lose electrons as readily as one might have expected them to. As you go down the group, the atomic size increases because number of shells increase. Potassium is 2,8,8,1, 4 shells. So that's period number 4. So that's the beauty of this periodic table. The position tells us so much about that element. The group number tells us the valence electrons and the chemical properties. The period number tells us the number of shells, which also affects its properties. All elements after 92, that is uranium, are artificially made in the lab. They cannot exist naturally in nature because they have very short half-life. They undergo nuclear decay very rapidly. They can't exist for a long time because the number of neutrons is far, far greater than the number of protons, which makes them very unstable. Before 92 also, there are many elements which are unstable or radioactive, like carbon-14 or the heavier isotopes of the elements. In fact, all elements after 82 are totally radioactive. There is no stable isotope at all. Before 82, at least we have stable isotopes, like carbon-12 is stable because number of neutrons, protons are equal. In sodium, we have 12 neutrons and 11 protons, 1 extra neutron, but that's okay because it's an odd number, atomic number, so that's allowed. More about radioactivity in higher standards. Now the groups, Manga GR. Elements of the same group have the same chemical properties. We know the reason why. And the atomic size also increases, as you can see. So there is some difference in the chemical properties. For example, down the group, it becomes more metallic, more reactive. So among the alkali metals, cesium is the most reactive. Francium theoretically would be even more reactive, but it is radioactive, so we can't really do experiments with it to check its properties. Among the non-metals, halogens, fluorine is the most reactive. So down the group, reactivity decreases. Now in this bullet is a GR. The reason why potassium is more reactive than sodium is because smaller the atom, closer is the valence electrons from the nucleus, more is the nuclear pull on the electrons. But if the shell is far away from the nucleus, the nuclear pull is less, and so the electrons can be lost more readily, more electropositive, better reducing agent, more metallic. The opposite is true for halogens. Bigger atoms like bromine, iodine, electrons are far, valence shell is far, so they don't gain electrons as readily as a small atom like fluorine. Fluorine is very small, 2,7. So the last shell is very close to the nucleus. The nuclear pull is great. They can accept electrons most readily, more non-metallic, more reactive, better oxidizing agent. Fluorine and chlorine are gaseous, whereas iodine is a sublimatory solid and bromine is a liquid. Highlight fluorine out here. So as you go from left to right, atomic size decreases. Yeah, 2,1, 2,2, 2,3, 2,4, all of them have same number of shells. But more the number of protons, more nuclear pull. So the last shell is closer to the nucleus. So fluorine is the smallest atom in period 2. Inert gases, well, because they are stable, some repulsive forces come into the picture, so they are an exception. They are not the smallest atom. The smallest atom in the whole periodic table is helium. Fluorine is the smallest. So in exam they will give you 4 or 5 elements and ask you to arrange in the increasing atomic size or decreasing atomic size. These are very tricky questions. You really think and answer them. Which is the largest atom in period 3? Sodium. Smallest is chlorine. So down the group atomic size increases, but from left to right across a period atomic size decreases. Noble gases are an exception. What about valency? Well, 1, 2, 3, 4, 3, 2, 1, 0 periods. Every period begins with an alkali metal. Of course, hydrogen is not an alkali metal, and ends with a noble gas. So from left to right, the valence electrons increase, and the valency fluctuates from 1 to 4 and then back to 0. State has to be learned. Bonding. Metals always form ionic bonds with nonmetals. Silicon is a metalloid, it will form covalent bonds with other metalloids or nonmetals. And the nonmetals will form covalent bonds. Inert gases don't form any bonds. Nonmetals will form covalent bonds with other nonmetals, but ionic bond with metals. Metallic oxides are always basic in nature. Aluminum is amphoteric, in fact, it can act as an acid or base, both, depending on the situation. Silicon onwards, their oxides are acidic. Phosphorus pentoxide forms high phosphoric acid when dissolved in water. Sulfur dioxide forms sulfurous acid when dissolved in water. Magnesium oxide is basic. Magnesium hydroxide is basic. Aluminum oxide is amphoteric. Their chlorides, learn the formulae. State has to be remembered. Bonding, again, metals are ionic. Aluminum is covalent. Actually, it's like a polar covalent, which is a hybrid between ionic and covalent. Electrons are shared, but there is a charge separation. And metalloids and nonmetals will form covalent bonds with chlorine. Same thing with hydrogen, the hydrides. State has to be learned. In fact, this is not so important. Mark it as read. Mark this as a GR. Why does atomic size decrease from left to right? Highlight the word nuclear pull. This is an interesting fun fact. It explains why aluminum forms covalent bonds rather than ionic, even though it's a metal. Because it's not a very strong metal, it doesn't lose electron very readily. Organization of the modern periodic table. Among these as read. Among the definition of representative elements. They are also called normal elements. The transition elements and the inert gases are not included here. Transition elements, mark the definition. I've explained this. Mark this as a give reason. Why they're called halogens? Because they are salt generators. They form acids with hydrogen, salts with metals. They are most reactive nonmetals. Inert gases, we know why they don't react. Mark it as a GR. Periods. There are 7 periods. Something interesting is the period 2 elements are called bridge elements because instead of having properties of their group, they show properties of the diagonally next group. So lithium is more like magnesium than sodium. Beryllium is more like aluminum than magnesium. The diagonal relationship, so they are called bridge elements. This is because of their extremely small size. So the greater nuclear pull makes them a little less metallic than expected. So mark this as a GR. The third period are called typical elements because they show the properties which represent the whole group. If you learn sodium's properties, you have virtually learned the properties of all alkali metals. So typical elements definition. First period is the shortest period, only 2 elements, hydrogen and helium. Second and third have only 8 elements. Fourth and fifth have 18 elements each because they have transition elements also. Sixth and seventh are the longest period. They have 32 elements each because they have those extra 14, 15 elements mentioned at the bottom, lanthanide and actinide series respectively. Mark this GR. Lanthanide series is called so because they are similar to lanthanum. Highlight lanthanum. Similarly, actinide series, actinium. Highlight actinium and mark it as a GR. Properties of representative elements. That is 1, 2, and 13 to 18. They're all metals, good conductors. Non-metals are on group 16 and 17. They are bad conductors. So from left to right, metallic property decreases and non-metallic property increases. What about transition elements? They are metals with high densities, high melting and boiling points. They are paramagnetic. That means they can be magnetized with electricity. They have variable valency and they form colorful ions and salts. Mark these examples as read. They are also used as catalysts like gold, iron, platinum. Mark this table as read. Very interesting. But these names are obsolete. New names have been given by IUPAC organization. All of this is useless. Now, alkali metals, group 1. Mark the GR. Francium is radioactive, so the most reactive title will go to cesium. Physical state, they're all solids, but they're soft. They can be cut with a knife. Good conductors of heat and electricity. Light elements. Francium is the heaviest. They have low melting and boiling points, and it decreases down the group. Cancel the values. As you go down, the size increases. Metallic nature increases as you go down the group. They become more electropositive. They lose electrons more readily. Valency remains the same, 1. We can form alloys from them. They are very reactive, so we can't find them in free state. Like sodium, pure sodium is not possible in nature. It's always in a compound state. Action of air, well, we should store them in kerosene. Market as a give reason because, as I said, they're very reactive, so they will react with the air, moisture, oxygen. They will get tarnished. Mark this GR. With hydrogen, they form ionic hydrides like LiH, NaH, etc. With water, they form hydroxides very vigorously. For example, sodium floats on water with a golden flame, starts burning the hydrogen. So exothermic. Potassium gives a lilac flame. With halogens, they form ionic halides like sodium chloride, potassium chloride. They're all reducing agents because they lose electrons. Alkaline earth metals are also very similar to alkali metals, but they are a little less reactive. Radium is radioactive. Physical state, again soft, can be cut with a knife. A little harder than alkali metals. They also form alkalis, they are oxides. But they are a little less soluble in water. Good conductors of heat and electricity. Density, more than alkali metals. Melting and boiling points are again more than alkali metals. Mark the GR. Size of atoms, again, as you go down, the atomic size increases. From left to right, atomic size decreases. So alkali earth metals are smaller than alkali metals because of greater nuclear pull or nuclear charge. Nuclear charge means number of protons. Mark this GR. Metallic nature, mark the GR. They lose electrons readily. Valence is 2. As you go down, metallic nature increases. Action of air, wrong information here, cancel it. Just know that they form stable oxides. With water, they form hydroxides, but not as readily as alkali metals. You may have to heat the water or use steam to make them react. With hydrogen and halogens and hydrogen, they do form ionic compounds. These are general reactions. Remember, these alkali metals have valency 2. So crisscross method, MH2. So beryllium hydride will be BeH2. Beryllium hydroxide is amphoteric. Fun fact. You know, these metals give a particular color to the flame. Sodium, golden yellow flame. Calcium, brick red flame. So learn all these colors. Halogens, salt generators, physical state, well, these are gases, this is a liquid, this is solid, sublimatory solid, it sublimes. Acetine is radioactive, so we don't study it much. Learn their colors as well. Conductivity, obviously non-metals, so bad conductors of heat and electricity. Non-metallic in nature, which decreases down the group because atomic size increases. Low melting and boiling point, but increases down the group. They are very reactive. Fluorine is the most reactive, marked as a GR. Oxidizing properties, Mr. No. Metals are reducing agents, non-metals are oxidizing agents because they easily accept electrons. Fluorine is the strongest oxidizing agent. Learn these equations. With hydrogen, they form covalent bonds to form the respective acidic gases, strong acidic gases. Hydrogen iodide, when dissolved in water, forms the strongest acid among these. With alkali metals, they form ionic compounds. Learn these equations and practice them for homework. Noble gases don't really react because they are stable, the last shell is complete. Only under extremely high temperature and pressure we can force them to react. They're all monoatomic molecules. Mark this as a give reason. They have very low melting and boiling points because they have weak intermolecular forces or interatomic forces. In this case, atom and molecule is the same. They have some uses, like helium is used in balloons. It's lighter than any other gas except hydrogen. Argon is used to fill light bulbs so that the tungsten does not get oxidized. Xenon is used in anesthesia. Radon is used for radiotherapy, medical purposes. We have neon lights, or rather noble gas lights, because each noble gas has a distinct color when electricity is passed through it. The sun, the stars are made up of helium. Chapter review, solve it perfectly, and all the exercises at the end of the book, solve them as well. You have to think a lot. Now, there are two properties which are in 10th standard. I would like to just explain it. ionization potential and electron affinity. Ionization potential is the energy required to remove the electron from the last shell of an atom. And electron affinity means the energy released when an electron is added to the last shell of an atom. So from left to right, both ionization potential and electron affinity increases. Because metals require very less energy, they will readily release electron. So IP is less. Whereas here, to remove electron, you will require a lot of energy. They want to gain electron. Similarly, if you add an electron to the last shell, it won't release that much energy. They are not so happy about accepting an electron. So electron affinity is low. But here electron affinity is high. They would be very happy and release a lot of energy when you add an electron to the last shell. Down the group, IP and EA decrease because the atomic size increases. More about this in 10th standard. From left to right, electronegativity increases because metallic property is decreasing and non-metallic property is increasing.
Hi students, this is AJ sir. If you found this video useful, press the like button. Also, if you'd like to enroll for my test series or online lectures, email me or message me on Instagram. Check my description for more information.